All right, we're now recording and we're covering major concepts for our unit test. This is a review of our functions unit, which is chapter 1 in your textbook. So our first thing is recognizing functions. Can we state whether each is a function or not and how you know? Now when we're doing this, I'm going to use like a green check mark to say yes, it's a function, or a red X to say no, it's not a function. Okay, so that's what that's going to mean in this lesson if you see the green check mark or the red X. On this one I've got a graph, so I'm going to use my vertical line test. So I'm going to get myself a vertical line. Now these ones are in red, so I think I'll use green for my vertical line this time. Nice lovely green. And so I'm going to use this vertical line, and I'm going to try my vertical line test to see whether things are functions or not. So here's my first one. I'm going to move my vertical line over that, and I can see that I'm only ever touching the graph at one point. I'm never touching 2 points on the graph at the same time. So that first one is a function. Check mark. For B, I find that I can touch 2 spots on the function at the same time. So what essentially that is I've got an x value, like say x is -2. It has 2 y values that correspond to that. Same for x is +5. I've got 2 y values that correspond to that. I'm touching the graph in 2 places at once with my vertical line, so no, not a function. Same thing for this sideways quadratic. I can hit 2 points at once, so not a function. This sine wave, I can only hit 1 single point at a time, so yes, it is a function. So let's do our final assessment. Yes, that's a function. Yes, that's a function. No, it's not. No, it's not. So that's my vertical line test. Here's my next one. This is mapping diagram. State whether each is a function and how you know. Now for a lot of these, I'm recording this, so I'm going to do a bunch of this verbally rather than putting a whole bunch of text. So just keep that in mind, that if you're looking at the PDF of this lesson later, a lot of this I'm just going to do kind of verbally. So one on the left, let's have a look at that first. I noticed that the 2 is mapping to 2 different y values. So that one is going to be not a function. So it gets a big red X, not a function. Because one of our inputs has got 2 different outputs. For our next one, for 1 it maps to 3, 2 maps to 1, and 3 maps to 1. So each input has a single output. So that is a function. So that gets a nice big check mark. So those are mapping diagrams. Here's our next one, tables of values. Which one is a function, which is not, and how do you know? For my first one, I'm looking at my x values. I'm seeing they're all unique. So I don't have any x value that's mapping to 2 different y values. So that one is a function. For my second one, I see 0 can map to -1 or +1, and I see that 3 can map to -2 or +2. So that one is not a function. Because I can have an input like 0 that would give me 2 different outputs, like -1 and 1. Okay, our last one, we've got -1, 0, 1, and 2. They all map to 5, but that's totally fine because each input has a single output. So that one is a function. It's good to go. Okay, next one. This is function notation. So we're now doing function notation. We've got 2 functions. F of x is equal to 2x minus 1. And g of x is a quadratic. It's equal to x squared minus 3. So I'm going to use function notation to find the value of each of these questions below. So for A, it says f at 3 plus g at 1. So what that means I'm going to do is I'm going to take my f function right up here, and I'm going to write it, but anywhere there was an x, I'm going to put a 3 instead. So 2 times 3 minus 1. And then I've got my g at 1. So I'm going to take my g function, but anywhere there's an x, I'm going to put a 1 instead. Now it's just a bit of algebra. Inside my first bracket, 2 times 3 is 6, minus 1 is 5. And in my second bracket, 1 squared is 1, minus 3 is negative 2. So 5 plus negative 2, that's the same as 5 minus 2. The answer is going to be 3. Okay, my next one. I've got g at y plus 1. That means anywhere there's an x, I'm going to substitute in y plus 1. So let's get my function here. Anywhere there's an x, I'm going to substitute in y plus 1. Now, I could leave it like this, but I think I want to simplify. So y plus 1 squared is really y plus 1 times y plus 1. Let's do my multiplying through the brackets. Everything in my first bracket gets multiplied by everything in my second bracket. Call that FOIL, first outside, inside, last. Y times y is y squared. Y times 1 is y. 1 times y is y. 1 times 1 is 1. A lot of students will say 2. It's not. Don't accidentally add. Minus 3. So collect our like terms. Y squared plus y is 2y. And we got plus 1 and minus 3. That's going to leave us with minus 2. So that's the expression we end up with when we substitute y plus 1 in for my function g. Okay, my last one, this one's a little tricky. We've got our f function, and the thing we're going to substitute into that f function is whatever we get when we substitute negative 2 in for g. So we've got to do the inside part first. What do we get when we substitute in a negative 2 for g? And then whatever our answer is, we're going to substitute that into our f function. So this is a little tricky. So I'm going to say, okay, I'm going to keep my f function, but I'm going to put in g at negative 2. So anywhere there was an x, I'm going to put in negative 2. So here we go. All I did was take my g, put it in there, but where there is an x, I put a negative 2 instead. So let's work that out and see what we get. Let's see. Negative 2 squared is going to be 4, positive 4. Minus 3 is going to be 1. So the answer is 1. So now I need to find f at 1. That means my f function over here, I'm going to use that now. I'm going to put a 1 in wherever there is an x. So that means 2 times 1 minus 1. 2 times 1 is 2, minus 1 is 1. So my final answer is 1. So that's a tricky combination. Okay, so that's function notation. Good thing to ask yourself right now is how comfortable do I feel with all of that? Could I have done all 3 of those without trouble, or is this an area I'm identifying that I need to work on? Okay, so function notation. Here is our parent functions. Our parent functions. Now, we will usually use Desmos to sketch these. I'm going to go to Desmos for a moment and share those with you, and then we'll talk about how we might use those. So let me see if I can find a Desmos here. Okay, here comes our Desmos graph. Sorry folks, this takes a minute to fill up this space. Okay, good. So here we go. Let's start with our first one. F at x, let's do our quadratic function. I'm going to say equals x squared. So that's my quadratic function. If I ask for a table of values, it does it from -2 to +2x values. And we substitute those in and we get a nice little pretty graph. So that's our first parent function. Our next one, which we are bound to see, is our square root function. So let's hit the square root and put an x underneath there, and here's our square root function. Now this one, when we try and do a table of values, it has a lot of trouble with it. There's nothing in the negative x direction, so we should probably just get rid of those. And our table of values is not great because when we substitute it in a 2 squared is 1.414236. That's not great. Let's put in values that we know we can take the square root of. So I know I can take the square root of 4, and the answer is 2. I know I can take the square root of 9, and the answer is 3. I know I can take the square root of 16, and the answer is 4. So those are nice, easy points to put on there that would allow us to know where stuff is quite easily. We also had our reciprocal function, so that is 1 over x. It's the one that looks kind of like this. It's got these two sloping things in quadrant 1 and in quadrant 3. And for this, 0, 1, 4, 9, and 16 is not great. So we notice that when we try and put in a 0 for x, it says undefined because the graph doesn't exist there. So that's a little bit of a problem. Putting in points of -1, 1, 2, those are great. And those can make graphing pretty easy. So this table of values turned out, just the auto-generated one, turned out pretty effective for us. What's the one that I'm missing? I'm missing, oh yeah, absolute value, right? Let's do our absolute value function last. In Desmos, we have in our keyboard, there's this little thing with the lines there, so I'll put an X in the middle. And absolute value just means always turn it positive, right? We're always going to turn whatever's in the brackets positive. That's what our absolute value means. So instead of a straight line, we end up with a thing that looks like a V. So those are our parent functions, and we need to be able to recognize those. Using Desmos to graph those and understand what they might look like, that's also important and helpful. So those are our 4 major parent functions. When we're talking domain and range of functions, remember when we're talking about domain, we're talking about all the possible x values that would make the function work. X values we could put in where we'd get an answer. If you take your reciprocal function, which is this one right here, and you try and put in a 0 for x, 1 divided by 0, your calculator will tell you that's undefined, or it'll say error. So that's an example of something that's not in the domain. It's not one where that function works. Of course, the range is our y values that we get when we plug in x values. All right. Let's talk about domain and range, and let's do it for some different kinds of things. Let's do it for some just ordered pairs, and then we're going to do it for some functions. So let's put a screen on here so we can kind of limit what we're seeing a little bit. There. Okay, let's start with my first one. I got to do my domain and range. So my first one, I say, okay, domain is all possible x values. So I do my squiggle bracket. My x values in order looks like there's a 2, there's a 4, there's a 6, and there's a 10. So 2, 4, 6, and 10. Those are my x coordinates. For my range, what are my possible y values? Looks like my lowest one is a 1, and then I got a 2, and then I got a 3, and then I got a 5. If something appeared twice, I would just only list it once. Okay, so that's my domain and range for ordered pairs. Easy, nice. My domain and range for this is one of my parent functions that's been transformed a little bit. So I'd like you just to take a moment and picture in your head, while I take a delicious drink of tea, what would this transformation of this parent function make it look like? Okay, so hopefully you said there's a +4 that's in with the x. That means it's going to move it horizontally. I remember the plus, it actually moves it in the opposite direction, so that's going to move it to the left 4. So it's going to actually start with an x-coordinate of -4 instead of an x-coordinate of 0. Let's go to Desmos and see what that looks like. So we're going to have our square root function, and we're going to say x plus 4. So here's what it looks like. Now what would you say about the domain, the possible x values? Looks like you can't have anything left of -4. But anything bigger than -4 is a go. It also looks like for y values, you can't have anything less than 0, but anything greater than 0 is a go, is good. Okay, so let's try writing that out in the proper domain and range set notation. Our domain is our x values. So first of all, it's not points, so we have to say, well, in between the boundaries, x could be anything. Like we could pick any real number. Any decimal number would be fine, but such that there's some limits. X has got to be greater than or equal to -4. It's got to be bigger than 4. Anything equal to or bigger than -4 is good. Anything less than that doesn't appear on our graph. Would not be in the domain. Our range, we're going to say something very similar. We'll do squiggle bracket. We'll say y is an element of real numbers, because it's not just points. It's a curved line where you could pick anything in between points, such that y is greater than or equal to 0. So we could have y equal 100 or 1,000 or 1,000,000,000, but it can't be anything less than 0. It can't be a negative number. Okay, so far so good. Let's look at our last two down here. We've got a quadratic and we've got a reciprocal. So for our quadratic, I see this is just x squared, but it's also got a +2 tagged on the end. That means it's going to be a quadratic that's moved up 2. Now I know with quadratics, I always know my domain is going to be easy. I know my domain is just going to be any number you want is good to go. So I'm going to say x is an element of real numbers. And how do I know that? Well, let's go to Desmos and have a look. So there's my quadratic. And this one was it +2? I think it was +2. Is that right? Yeah, +2. So we see it's getting wider and wider and wider and wider and wider as we keep going up and up and up and up. And you could put in any x value you want. If I got my table of values, I could put in an x value of 100 and I get an output. I could put in an x value of 1,000 and I get an output. I can put an x value of whatever that number is and I get an output. So any x value is good to go. Y values, not true. I've got nothing below 2, nothing below +2 on the y-axis. So for any quadratic, for domain, it's really easy. It's just can be anything. Our range, we say y is an element of real numbers, such that y is greater than or equal to +2. Nothing below -2. That would not be on our graph. Okay, our last one is the reciprocal function. This one's a bit trickier. You remember that this one has like 2 parts to it. So our reciprocal function looks like that. So we know for our x values, it could be anything in the negatives or in the positives, but it can't be 0. There's nothing there at 0. But this isn't actually the function we're dealing with. It's a bit changed. It's 1 over x plus 3. So that plus 3 is in with the x. That tells me it's a horizontal shifter, left or right. And since it's a plus, that tells me it's actually going to go in the negative direction. Because for our horizontal shifter, it works opposite. So it's going to actually shift it to the left. So let's get Desmos back up here, and let's add that in. There we go. So it's the exact same graph. It's just been shifted left 3 spots. And now I notice the spot I can't have is not x value of 0. It's an x value of negative 3. If I try and put in an x value of negative 3 into my table of values, it tells me it's undefined. There's nothing there at x equals negative 3. Similarly, with my y values, I could have anything. It keeps going up and it keeps going down. But right at y equals 0, there's nothing there. There's nothing there. Okay, so let's write those out. I'm going to say my domain is x is an element of real numbers such that x cannot be negative 3. Anything is good except for negative 3. You can't plug that in. It doesn't work. For a range, same deal. Y could be anything except y can't be 0. There's nothing there. It's not on the range of our graph. Okay, so you might find it helpful when faced with something like this to go to Desmos, graph it, and have a look. Or you could just think about what the transformations are and just picture it in your head or sketch it out on paper. Any of those are great options for figuring this out. Okay, thanks for hanging in with me, folks. Here we go. We got a little more to do. It looks like the smartboard might be struggling a little bit here. So give me a moment to see if I can get this worked out, and if not, I'll have to reopen the file. I'm just going to pause our recording for a moment. Recording again. Okay, we're back at it. One of the things I had was graphing the inverse. We've already done that today, where you draw the mirror line and then you put points on the other side. So I think I want to skip this one, because that's one we already did today. Let's do a quick practice of this, because I think we definitely need a little bit of work on this based on the things on that practice quiz. Determine the inverse equation of the following. So we've got a couple of functions here, and we want to find our inverse. So first thing we do is we write it as y equals negative x plus 8. So we take it out of function notation for the moment. And then we put a line here to show that we're changing gears. We're going to switch our, and actually let me change colors too to make it really obvious. And now we're going to switch our x and our y. So this is no longer the same function. It's now the inverse function when we change our x and our y. But we want to clean it up and write it as a y equals something. So first of all, let's subtract 8 from both sides. And now let's divide both sides by negative 1. There. Okay. So this is our reciprocal function. Let's write it like that. You could have written this as 8 minus x. That's perfectly good as well. And we'll put a nice little box around that. So we've now found the inverse. So you show me that, yep, I got it. I found the inverse. Here's my final answer. Now for our next one, g at x, let's find the inverse of that. So let's write it again as y equals 4 squared x plus 6. Let's put a line to show that we're changing gears. We're going to write the inverse now by switching the x and the y. So x goes here, y goes here, and now we need to solve for y. Let's start by subtracting 6 from both sides. Now let's divide both sides by 4. And you might think, hey, I'm done. I isolated the y, but you haven't. The y is squared. So we got to take the square root of both sides. That's going to leave us with y equals the square root of x minus 6 over 4. But we got to remember it could be plus or minus, right? Because when we take the square root of 4 could be 2 or negative 2, because both of those things, when you square them, give you 4. So we got either plus or minus. And if we graph that, of course, the plus part is going to be like this, and the minus part is going to be like that. So that creates the two halves of our quadratic. So this is basically just a quadratic turned on its side. That's the inverse. Okay, so that's done. Let's put a box around that. You might have said, hey, Mr. Roy, can I divide the x by 4 and the negative 6 by 4 and write it so it looks a little more like slope and y-intercept format? And I would say, sure, that's not wrong, but that's not going to make this any clearer or neater, so it's probably best to just leave it like it is. Okay, awesome. So we determine the inverse equation for those. Here we've got some transformed functions. I started with a parent function and then I did a bunch of transformations to them. What are those transformations? What are those transformations? So for each function, we're going to identify the parent function and we're going to describe how the graph of the function can be obtained from the graph of the parent function. So I'm going to do a bunch of this verbally by describing what we would do. But the first thing I want to have a look at is what's the parent function of each of these. So what do you start with as your base function? So I'd like you to look at A, B, and C, all three of them, right now, and I'd like you to think about it and see if you can identify what parent function would go with each of those. Okay, so we've tried to identify which would go with which. Let's write in what our parent functions would be. So I'm going to just say PF in this row is for parent function. So for this one, our parent function is, and let's write it in function notation, because that's a nicer way to do it. This is going to be just x squared. A quadratic is going to be our parent function. And I can tell that because there's my squared right up there. My next one, my parent function for this one, is the radical function, which is just the square root. And I can tell because there's a radical sign, a square root sign in there. And for my third one, my parent function is going to be the absolute value function. Okay, so I've identified the parent function for each of those. Now I need to talk about how we would get there and what we would do. So this part I'm going to do kind of scrawl some notes and I'm going to do it verbally, but I'm not going to write everything down on the page because that'll take a lot of writing and I kind of want to move things along at a good pace here. So let's get my red pen ready and let's have a look. The first thing I see is let's have a look at what's happening to my y values. This is going to affect my y values and this is going to affect my y values. Right in front, I've got a negative sign. So that's going to be a reflection in the x-axis. It's going to be a reflection in the x-axis. My next thing that I've got is the 2. I'm going to multiply all of my y values by 2. So that's going to be a vertical stretch by a factor of 2. Next, I see this 1/8. What I do with that when it's in the brackets, when it's in front of the x like that, I'm going to divide all my x values by that number. Now what happens when you divide by 1/8? That's the same as multiplying by 8. So I'm going to multiply all of my x values by 8. Or you could say divide all of my x values by 1/8. But that's a bit tougher to do. That's going to create a horizontal stretch by a factor of 8. So it's going to stretch it out horizontally. Last one. Back here, that's my y value, my +1. That's going to just shift it vertically up 1. So it's going to shift everything up 1. We could type all that into Desmos, and we get ourselves a nice, lovely graph of those transformations. But you're going to have to be able to describe them too. This next one has a trick. It has a trick. So I'm going to go green here. And here's the trick. Inside the brackets, things need to be factored. So I'm going to write it as y equals square root. Now I've got -3 and I've got 9. I can actually divide a -3 out of that. Okay. So I see from this, what are my transformations? I've got nothing out front, so I'm not reflecting in the x-axis or multiplying my y values by anything. I've got this negative right in here. That means I'm going to reflect in the y-axis. And why that happens is I'm going to multiply all of my, I change the sign essentially of all of my x values. I'm going to divide all of my x values by 3. And my shifter, I'm going to move my graph 3 units right. That's in the positive direction. Move my graph, so I'm going to move 3 units right. And this one, finally, that affects my y values, and we just do it as is. I'm going to move everything down 2. Okay, my last one, I've also got to do a factor on this one. Got to factor something in the brackets, so we'll say y equals 1/2. I can factor out a 2 and say x minus 1. So what are we doing here? We're multiplying all of our y values by 1/2. That's the same as dividing by 2. So a vertical compression by a factor of 2 or a vertical compression by a factor of 1/2. However you say it is fine as long as you say compression. I can tell it's getting squished. We're going to divide all of our x values by 2. So that's a horizontal compression by a factor of 2, meaning we divide all of our x values by 2. Our horizontal shifter tells us to go right 1 unit, and our vertical shifter tells us to go up 3 units. Okay, so we've described the parent function, and we've described everything we would do to each of those to go through all those transformations. All right, we're on the home stretch now. Thanks for hanging in there, folks. I know this is a long piece. The 0.26 is on the graph of y equals f of x. So it's on our graph. We don't know what the function is, but we know that point is on there somewhere. State the coordinates of the image of this point on each graph. So we got our basic graph. We know the 0.26 is on there, and then we're going to do a bunch of transformations. So we got to figure out what's going to happen. First things first, I know I'm multiplying all of my y values by -5. I'm multiplying my y values by -5. I'm dividing my x values by 4. And I'm adding 1 to my y values. So let's write out what that would actually look like for our point. Our point is 2, 6. Well, my first operation, I'm saying, okay, I'm dividing my y values by -5. So let's take my y values and divide them by -5. And this one says oh no, sorry, multiplying. My bad. I'm multiplying all my y values by -5. There we go, that's better. And then this one says I'm dividing all of my x values by whatever that is. That's a 4. And then this one says I'm adding this to all of my y values. So let's add that to my y value. So what does that work out to? 2 divided by 4 is a half. And 6 times -5 is -30, plus 1 is -29. So that's what that transformation does to that particular point. Let's try our next one. Again, so my point is 2, 6. This one tells me I'm going to multiply all of my y values by a third. That's the same as dividing by 3. I'm going to need to factor this, so I actually am ending up with 2 times x minus 1. So the 2 tells me I'm dividing all of my x values by 2. The -1 tells me I'm shifting in the positive direction for my x values. So I've got to add 1. And the +4 tells me I'm adding 4 to my y values. Yeesh, so what's that going to work out to? 2 divided by 2 is 1, plus 1 is 2. 6 divided by 3 is 2, plus 4 is 6. So this one actually doesn't change. This point is called an invariant point. So it's one of these points that when it goes through the transformations, it doesn't actually move. It happens to be on both our parent function and on our transformed graph, which is kind of neat. Okay, our last one. You folks have been hanging in there really well. Last one I want to go through to help prepare you for our test tomorrow is this. So take a look. Okay, so for this one we're determining the equation of the transformation of the parent function and state the transformations on the function. So I'm going to state the transformations just verbally first, and I'm going to kind of circle stuff as I go. Oh, no, I want red. I don't want blue. I want nice bright red. There we go. Okay. Multiply all your y values by a half. So that's the same as dividing your y values by 2. That's a vertical compression by a factor of a half. Shift everything to the right 2 units. Shift everything up 4 units. Now let's actually write what our equation would look like. So we're starting with a parent function of a quadratic. F of x is x squared. Let's write our transformed one. It's going to look like this. It's going to start with g of x. And so I notice I have a half out front and I have a +4 at the end. Now this part is where my function is going to come in. My function is x squared. So I'm going to have x minus 2 anywhere I would have an x squared. So that's going to be the actual transformed function, whereas this just tells me what to do. It doesn't actually tell me what the function would look like. It just tells me the transformations. Okay, last one. Let's describe our transformations. First one, multiply all your y values by 2, so vertical stretch by a factor of 2. And move 3 units left in the negative direction. Okay, so let's write our function. We're going to say g of x is going to be, well, it's a 1 over x. So let's put the 2 first. There's nothing added to the y. Anywhere there was an x, we're going to put x plus 3. So that's it. But I could multiply that 2 through the brackets and end up with 2 over x plus 3. So this, I took my basic function, my parent function, and I did these transformations to it. And that's my new equation. Okay, whew, that's a lot of stuff. That's a whole unit. And I've been talking at you for a long time, which I know you may be hitting the point where you're like, starting to shut down. But I wanted to have a good recording of all of this stuff to help you with your studying. I'm going to stop our recording there.